kilogram and make this 0.1 kilograms. All right, what is the acceleration now? Ignore friction. All right, so this one clearly more difficult because I have the object. Not only do I have different objects here, I have two objects, but I have them going in different directions. First off, that 0.1 kilogram mass, which way is that going to move? Okay, and the cart, the thing with wheels? Okay. When I have things that are moving in different directions, but they're tied to each other, this is some sort of string. It's an ideal, perfect string, so it's not going to stretch. It's not like that's going to stay there and this is going to suddenly bungee jump. So this is going to move to the right, and that's going to move down. What force is causing the whole system to move? Tension's not causing the whole system to move. If I snip the rope, part of it would still move.
Weight.
I got several objects here. The weight of what is going to cause this whole thing to move?
The box. The box.
Yes. The weight of this is what's going to drive the whole system. So that net force, again, plug it into mass times acceleration, that net force is the weight of this box. So this is the weight of box. What is the mass that's going to be accelerated? Are you stopping there?
To the right.
Need more. The 1 kilogram mass will accelerate. I agree with that.
Excuse me.
Okay. Is that it? Only the 1 kilogram mass is going to accelerate? So I'm going to set it up and suddenly that cart's going to be moving to the right. And nothing else is going to move.
And the 1 kilogram.
Yes, yes.
So plus.
They are both moving. Both of these masses are going to accelerate. So the mass, total mass here is going to be, well, mass of cart plus mass of box times acceleration. Formula for weight.
Gravitational pull.
Weight is gravitational pull.
Mass times gravity.
Let's work on the wording. I think you would have written it down correctly and solved it correctly, but it's mass times. There we go. Yeah. It's the tiny, remember, gravity huge. We're just looking at a tiny piece of it. All right, so m times little g is equal to that. So this is the mass of the box, because it's the weight of the box, that's what's driving it. The weight of the cart is not causing this thing to move, because the weight of the cart is acting this way, and I got a normal force countering that. So this is 0.1 kilograms times 9.8 meters per second squared is equal to 1 kilogram plus 0.1 kilograms times acceleration. So 0.98 equals 1.18. So A is whatever that is. Yes,
What the vector gonna be on top of the A's?
okay, so let's talk about that. Both of those objects are going to move together in an ideal string and even a mildly ideal string. The 1 kilogram mass is, if it moves 2 centimeters, the box is gonna move 2 centimeters. They will move the exact same distance in the exact same amount of time. They're only moving in each movement, that's gonna only move down, that's gonna move to the right, they each move in only one direction. Their speeds will be the same. Velocities won't be because they're in different directions. But the speeds are the same, the distance they travel is the same, the scalar acceleration is the same. Technically, the acceleration of this one is to the right, and the acceleration of this one is down. But since they have the same acceleration, I dropped the vector symbol just to indicate the magnitude of the acceleration. Which might seem sort of a cheat, but it's what I did. I would need to be more explicit, but this is a situation where if I ask for the acceleration, since the directions are different, hopefully you would know that I'm looking for magnitude here. But if we really wanted to get picky, the acceleration of this is 0.89 meters per second squared to the right, and this is 0.89 meters per second squared down. All right, let's do another one of these. So what I'm gonna do is I'm gonna put an additional mass onto here. That is a 0.5 kilogram. What will the magnitude of the acceleration be now? Or how do you find it? What changes? I assume someone's about to shout out great confidence and answer.
Just the mass. Just the mass changes,
Okay. Yep.
so it'd just be 1.5 instead of 1.
That would be 1.5 instead of 1?
Yeah.
Yes.
Would it be 0.1612?
Say it again,
162
0.162.
meters squared? No, or meters squared.
I'll throw a per in there also, meters per second squared. That number doesn't sound right.
It's supposed to be, is it 1.6?
1.6?
If you add 5.5?
Yeah, this would be 1.6 here. So 0.98 doesn't change. So 0.98 divided by 1.6, pretty sure it's not that.
Yeah, 0.6.
Say it again,
0.6125.
0.612. Did I miss here?
Huh?
Did, those numbers seem to be flipped.
Oh,
6.1?
probably did my math wrong.
2.5.
And the lesson there is, show your work. Please, please, show your work. All right. Now let's see if any of this makes any sense there. The fact that my driving force doesn't change, but I now am moving a lot more mass, so I would expect the acceleration to be less. It's a lot harder to move more mass, and so the acceleration is indeed less. Ready for me to change the problem again? I got some nods on that one. Whew. feel the excitement. All right, so this was moving, parenthetically, this was 1.1 kilograms. And this was 1.6 kilograms. Let's throw another half kilogram on there. 0.5 kilograms. What will the acceleration be now? Or how much mass am I moving now?
Well, 2.1.
Yeah, the whole thing, 2.1 kilograms. And the magnitude of our acceleration now?
2.058 meters per second squared.
So I added more mass and it accelerates faster?
0.46 repeating. Oh, I multiplied.
0.46 repeating? Did you have it
Yeah,
flipped?
I multiplied.
Okay.
So I got that.
All right. Now, let's check out, not what I wanted. Everybody loves a graph. All right, so we are going to, let's see, what did we adjust? We adjusted the total mass, and then we measured acceleration. So if I did acceleration, the magnitude of acceleration versus mass. That's the plot I'm doing. Delicately drawn. This is my acceleration. Make it look proper. Acceleration in units of meters per second squared. And then mass. In kilograms. So if I make this 0.25, 0.5, 0.7, 1.25, 1.5, 1.75, 2, 2.25, should be enough. And then my acceleration, let's see, 0.1, 0.2, 0.3, 0.4, 0.5, 6. All right. So we have a data point there that when my mass was 1.1 kilograms, that my acceleration was 0.89 meters per second squared, so 1.1 and 0.89, so I got a data point there. Then if I had 1.6 kilograms, which is about here, it's 0.612. And then if I had 0.46, 2.1 kilograms and 0.46, so somewhere around there. Now I know my drawing's a little bit off, but that's not a straight line. And we're dealing with perfect numbers over there, so something should be straight. This actually is curved. Apparently a second line is drawn. So the question is, how can we graph this so this actually looks right? So we can actually do analysis. That's better wording. Well, let's think about what we're testing here. We're looking at F equals ma. Go back to the line. This is y and x. I have a line. What is the generic equation of a line? I know it's been a while for some of you, but some of you should be a little bit fresher. Yep. That is the generic equation of a line. And again, I don't care for m because we use that for other things, so I'm just going to instead use the $ sign for slope. This is the slope-intercept form. So what I want to be able to do is I want to get that equation into something that looks kind of like that. Well, this is mass, and this is acceleration. So I want to solve for A. A is force divided by mass. But it's still not quite in that form because I have mass over there, so when A is equal to the force times 1 over mass. Remember, when you multiply fractions, let's flash back to that. If I have 2/3 times 4/6, how do you multiply fractions?
Cross multiply?
It depends on what you mean by that. You mean multiply across or do diagonals?
X. Is that like that?
That's when you have two fractions with an equal sign in between.
Okay.
When you're multiplying fractions, you multiply across.
Right, yeah.
So the numerator would be
18. Wait, 8.
Eight.
8 over 18.
8 over 18, which you can reduce if you feel like it, or use a calculator. All right, so what's happening here is that I have, my answer is f over m. I'm claiming that f times 1 over m is f over m. And I can turn anything into a fraction by just dividing by 1. So f times 1 is f, 1 times m is m, so this is what we're working with. So if I plotted acceleration versus mass, I'm not going to get a straight line. I need to plot acceleration times versus 1 over the mass, the reciprocal mass. So we're going to redo this. So if my mass is 1.1 kilograms, what is the reciprocal? And I'll, so 1 over 1.1 kilograms. I need someone with a calculator to crank that out.
0.90. Oh, 90.
Times 1 over kilograms. The 1.6? Over kilograms. And the 2.1?
0.476.
All right. So now when I plot it, let's see, we're going from 0.4, so let's break that 0.1, 0.2, 0.3, 0.4. That will be my 1 over mass with units of 1 over kilograms. And over here, so this is acceleration versus, acceleration versus 1 over mass. And this is my acceleration in meters per second squared. And we had, all my accelerations, we had 0.89, so make this my 0.1. All right, so when my acceleration was 0.89, my inverse mass was 0.9. So 0.9, 0.89, somewhere around there. When my inverse mass was 0.625, my acceleration was 0.612. Somewhere around there. And when my acceleration was, or my inverse mass was 0.476, so somewhere around here, it was, my acceleration was 0.46. Now, not that you can necessarily tell, but those are supposed to be in a straight line. And the slope of that line, the slope, well, it's change in y over change in x, is going to be my acceleration over 1 over the mass. That's acceleration divided by 1 over the mass, which is acceleration times mass over 1, which is what? What is acceleration times mass? So when you do this experiment, which you will, when you do this experiment and you plot acceleration versus the reciprocal of the mass, or inverse mass, the slope of the line should be equal to the force, which is the weight of the hanging box. So if this were done perfectly, my slope should be 0.98 newtons. Because, now, when you do the lab, will it be perfect? I doubt it. Perfection usually raises suspicions in a physics lab. I can't remember if I told this story or if it's in the video of the group that had perfection.